Alright, so in this video we're going to talk about the new chapter, so we're in chapter 5, and we're going to talk about forces and motion. Okay, so the best way to understand what makes this unit different than the units we've done already, so for example kinematics, and then of course non-kinematics, which would be changing accelerations, calculus, and things like that, you can kind of umbrella them under this. And the thing about calculus was it told us how things move. Okay, whereas forces tell us why things move. All right. So we need to start with the idea of what do we mean when we say a force. Okay, so a force we can simplify as saying it's a push or a pull. Okay, it's the easiest way to say it. If you have an object that's kind of sitting around and you want to make it move, right? So basic idea, you have an object sitting here that's not moving. If I want to make it move, right, the only way you can do that is to, if there's something on there to grab, and you can pull it in a direction, or you can go up to the other side of it and you can push it. Okay, now when you read your chapter, you can read about how forces come in different flavors. You can have things like contact forces and non-contact forces, long-range forces, things like that. But we're just going to kind of hit the very basics in this video. Okay, so in that picture that I drew, we showed an object at rest, and we said that we can push or pull it. Now, one of the things you'll notice is when I said you either can pull it, which was this red line, or you can push on it, which we'll draw here in green. Okay, the direction that I push or pull is significant. Okay, you'll notice that each one of these had a line with an arrow on it. Okay, which means that when you push or pull something, there's two things to that, right? When I apply a force, it has some amount of strength to it, right? And it also has direction. Okay, and so what does that mean? Well, the direction should be the giveaway, but then the strength is what we would refer to as the magnitude. Okay, so that means that force is a vector. Okay, and so typically when we have an object, so here we said the box was at rest, what we do is we generalize the box as a dot. So this is the same box that we drew up here. Okay, and then if we want to draw some sort of force on it, well, we start by putting a vector starting on the dot and drawing it off in a certain direction. Okay, and what's important to understand is that it really doesn't matter if it's a push or pull. Either way, it's a force. So pushing or pulling is and they're the same thing. So it doesn't matter whether we say we pushed on it or pulled on it. Either way, there is a force being applied on this box towards the right. The length of that vector tells us the magnitude, and the arrowhead tells us the direction. Okay, now because force is a vector, there's a mathematical term we use called the superposition of forces. Okay, which is a fancy way of saying a vector sum of forces. Okay, so if I've got multiple forces acting on an object, then what we do is we have this new term that we use for the forces. It's called the net force. Okay, and in mathematics, the term net means total. So it's a total of all the forces acting on the object. So if I've got multiple forces, right, we've got, say, force 1, and then we have another force, say, force 2, and then we have another force, say, force 3, okay, and so on. The superposition would be the addition of all these forces. But keep in mind that each force is a vector. So each force has some x component and a y component. And it may be true that in one dimension, one of those components is 0. But either way, always think of forces as having two components. Okay, and in the end, what we end up getting is the net force as a vector. Okay, and that's what we mean when we say the superposition. So we can still add all of our forces together. And when we add them, we have to add them as like components, right? X's and Y's. Okay, so as we mentioned, forces come in different kind of flavors. Some of the main types that you're going to see in this class, we have gravity. You'll see springs. Okay, we have tension. Okay, a couple other forces too that we'll see that pop up: normal force, friction, drag, thrust. Okay, there's also other forces too, like nuclear forces and electromagnetic forces, but these are the essentials for mechanical forces. All right, so gravity, of course, we already know. It's a force downward, okay, and it's always towards the center of an object. So it's a force downward, which is relative to us on the planet. What we really mean by that is towards the center of Earth. Because no matter where you are on Earth, this force tries to pull you towards its center. Okay, which is relatively downward anywhere you're standing. Okay, now a spring force would be anything that's elastic. From, say, an elastic material. Okay, so this could be like a rubber band, or a typical spring. Okay, tension force would be in something like a string. So it's force from a string or rope. Perhaps a chain. The important thing is it's rigid, meaning it doesn't stretch or compress. It stays in its form no matter how hard or soft you tug on it. Okay, so that's the important thing, is that it's a rigid material. Okay, the normal force, okay, is a force that is perpendicular to a contacted surface. Okay, and we'll get more details on what these things mean later on. Okay, friction is a resistive force, and it's caused by contact, so it's resistive because of contact. Drag is also resistive, but this is usually due to air or some other fluid material. Okay, for our purposes, we're going to deal with drag mostly through air. And then another way to think about it is it's like air friction. And again, this could also occur in things like water and other fluid materials, but we're going to focus just on the air aspect of it. Okay, and then thrust would be a pushing force caused by like an engine, say like a rocket engine or something. Okay, so here's our main catalog of forces. And again, we're going to do plenty of examples of each of these. Right now, we're just kind of outlining how we could see the different ways we can look at forces. Okay, so one of the things you have to think about is how do we identify forces? Okay, so if I've got an object, how do I know exactly what forces are actually acting on it? And so they come directly from our catalog. Okay, and so one of the things we're going to do is, if I just go back to something simple, let's say we have a inclined surface with a object resting on that surface. Okay, resting, maybe it's moving, who knows. The point is, when we look at this object, we have to think about what forces are definitely on it. Okay, so one trick is to draw a little circle around the object. Okay, and anything that touches the circle, so anything touching the object inside the circle must be exerting a force. Okay, so when I'm looking at what's touching it, the only thing touching it is the surface right here. Okay, and so if we look at our catalog, well, what forces could possibly be caused by contact from the surface? Okay, well, one force that's definitely there is the perpendicular normal force. Okay, another force would be friction because of resistive. Now, of course, because it's resistive, we have to be careful and we have to know exactly which way the force is going. So, for example, which way the object's going. So if we have a box and let's just say it's moving up the ramp, so it has a velocity up that incline, then it follows that friction would be resistive, and it's because of contact with the surface. So we make a dot, tail end of our vector, and we would say friction goes in a direction resisting the motion of the object. Okay, and so since that surface was the only thing touching the box in the circle, we're done with our contact forces. Okay, so these two things represent contact forces. Now, are there any forces that are not contacting the box, but they would still be acting on the box? Okay, and the answer to that would be yes, there's also gravity. And remember, gravity is always straight down towards the center. So even though the incline is at an angle, gravity would still be straight down. Okay, and another way to think about whether or not gravity is there, gravity acts on anything with mass. Okay, so that brings us to another idea. Well, what do we mean when we say mass? Okay, now there's some confusion that students have with mass. And so the idea simply is that mass represents the amount of matter contained in an object. Okay. Now, I've heard students say it's the amount of space that an object takes up, but that's volume, because depending on how the mass is distributed in the volume, that's density. So when we refer to mass, it's just how much stuff is there, okay, how much matter is contained. And for our purposes in physics, we measure mass in kilograms. Okay, and you might have measured it in other things in other science classes, but since physics for right now, we're dealing with mostly large-scale, macro objects, kilograms tends to be a very good unit for us to quantify mass. Okay. Now, one of the other things we get when after identifying mass, and this is something that Newton came up with, and it was something called inertia. Okay, so inertia is the tendency for an object to resist a change in its state of motion. Okay, so you could think of it as, just to get a visual, if I were to have a large, say, train car. Okay, so say that this is a 1,000 kilogram train car. Okay, 1,000 kilograms is pretty large, and if it was sitting here at rest, okay, think about how much force would you have to apply to make this object move. Okay, no matter if I push on it or pull on it, if it's at rest and I want to make it move, it's going to require a lot of force. Okay, similarly, if you look at the same train car, but this time it's moving. So same train car, 1,000 kilograms, but now it's moving. And it could be moving at a very slow speed. It could be moving at 1 millimeter a second, right? Very, very slow speed. And if I asked you to stand in front of it and try to stop it by applying a force against it, that would still require a lot of force. So in either case, F is big, too big, in fact. Okay, but the idea is that inertia represents how an object resists the change in how it's moving. In the first example, it wasn't moving, so it has a tendency to stay that way. And the harder it is to change that state, the more inertia the object has. So in fact, a way to kind of think about inertia, okay, is inertia is very similar to mass. Okay, you could think about it as mass is the number or quantitative way of describing an object's inertia. Okay, so the more mass an object has, the more inertia it has. So that's kind of the easy way to do that.